good afternoon, everyone, or morning, wherever you are, and welcome to 0PM's next webinar. Today, we're speaking about global perspective in the persistence and mobility of regulated chemicals. So we have two speakers, but first I'll introduce myself. I'm Sarah Hale. I work for the German Water Centre, in case you don't know me. And together with my colleague Hans-Peter Arp, we're working on 0PM, which is a project funded by the European Union. And we're looking at interlinking prevention, prioritisation and removal strategies to protect the environment and human health from these persistent and mobile substances. So this is one of a series of webinars. You can watch the other ones on our YouTube channel. But today I'll introduce our two speakers. We have Sivani Baskaran and Raoul. They both work at InChI, which is the Norwegian Geotechnical Institute. Sivani is a Canadian NSERC postdoctoral research fellow, and she is looking at Bayesian statistical methods to analyse physical chemical property data. Raoul is an ecotoxicologist and environmental chemist, and he's focusing on the intersection between natural sciences, big data technology and statistical analysis for regulatory purposes. So they're going to guide us through our webinar today. If you have any questions, please pop them in the Q&A box. Hans-Peter will go through them at the end. We'll try and answer as many as we can. Any that we miss, we'll get back to you afterwards. We're recording the webinar and we'll pop it on the YouTube channel afterwards, so you'll be able to watch it. So I think I'm going to hand over now to Raoul and Sivani for them to start their presentation up.
Yes, thank you, Sarah. Just sharing the screen. Just a few seconds. Now you should be able to see the screen.
Lovely, yes.
People are nodding as well. That's good to see. And then I would also like to welcome everyone attending this webinar here live. It's appreciated. As Sarah said, today we are talking about the global perspective on the persistence and mobility of regulated chemicals. My colleague Sivani later on will have her presentation, but I will get things started with all of you today. Whoops. There we go. When preparing for this presentation, I came across this very neat overview figure from the official 0PM material, and I think it illustrates a very nice key point here on the environmental fate of persistent and mobile substances. That on the left side, of course, we have the chemicals, and some of them are used in products or in processes, and they ultimately end up in the environment or could end up in the environment, and that might have implication for water treatment, humans, and of course nature in a grander definition. But of course, what's clear from this figure, at least for me, what stood out is the chemicals are sort of in the center of all of this. And in order to protect the environment and in order to assess the persistence and the mobility of chemicals, we need to have a solid overview of what type of chemicals are out there and are they persistent or mobile. So in my presentation, I'm actually just asking a simple question: how many substances are regulated worldwide? As with many other rather simple questions, the answer is much more complicated, and the way to answer this question is much more complicated than the answer itself. And I will present this in the next few minutes, and I'm sure we can have a good discussion about that. To make things a bit more ambitious here, we did not only set out and try to identify how many substances are regulated worldwide, but we also want to know what their structures are. So we are on the hunt for chemical structures here. Before I go any further, I would like to take just a moment and acknowledge some of the great people that I had the pleasure to work with here in 0PM. Of course, on NGI side, my colleague Sivani, who's now wrapping up her postdoc, and Hans-Peter. But I was also fortunate enough to collaborate with Emma Szymanski from University of Luxembourg. Zhang from EMPA provided a lot of basis for the work I'm presenting today. And of course, Sarah Hale from the German Water Centre, TZW, is also very much acknowledged here. And none of the work I present here I've done alone. All of this is a team effort. So I just wanted to take this moment and acknowledge everyone. When we come back to the original question that I posed, how many substances are regulated worldwide? Let's first think about the word worldwide. I've shown you here a map of the world, and in color you can see regions or countries for which we have information on the regulation of chemical substances. You can see that we have data, for example, in Canada and in the US, here in Europe, in the Nordics, or in the European Union in general. We also have very good data sets, for example, for China and other Asian countries, and we have a lot of data from Australia and New Zealand. We have limited coverage in the countries that are in gray color, like Mexico, Turkey, Russia, or India as examples. But what I really want to highlight here when we talk about global perspectives is that for a huge part of the globe, just look at the African continent, the Middle East, large parts of South America here, we do not have any publicly available data to work with here. So this is really something to keep in mind with everything that we are presenting here, that we are essentially focusing on just a subset of the global situation. Now, those of you that might have seen this presentation before know that I will get into some form of a little rant here about the chemical data that is contained in official inventories here. And that is just to highlight the complexity of the task to assemble a good overview of the regulatory state on a global level. These different files, or come in various different formats here. So we have inventories. In an ideal world, they would be shared in a nice machine readable format without any strange characters, etc. Maybe even in a CSV file, and life would be so nice. We could just use these files and can just programmatically put them together, and then we know how many chemicals are regulated worldwide. That's obviously not the case. The data that we have access to comes in a variety of different formats. Yes, CSV files are one of them, but also Excel files. I'll talk about something related to Excel files in just a few moments, but we also have literally photo scanned copies in PDFs in thousands of pages. We do sometimes only have non-scrapable websites, so we actually have to manually copy paste. So that alone is a challenge we are facing. Then, of course, comes the problem with conventions, and that's especially true for machine readability. For the tools that we use, and I will present them in just a few moments, we have to use like high throughput methodology. And that also means that every type of information that we use has to be like well behaving from a machine readable point of view. That means that non-Latin characters are not great. When it comes to chemical names, for example, we often have Greek letters in them. And these can cause some of the tools that we use to hiccup. So we need to fix all that. So there's a lot of manual curation going on there. I was mentioning the challenge that we sometimes face with Excel, and as much as I'm tempted to talk bad about Excel, I actually think it's a wonderful tool. But those of you that have worked with CAS registry numbers before in Excel know about this like notorious feature Excel has of transforming CAS registry numbers into dates. And things like these obviously propagate and are hard to fix, but we actually wrote a couple of algorithms where we try to repair faulty CAS numbers as much as humanly possible. There we go. The other part, when we talk about chemical data and inventories, is of course, remember the extra question that I posed. We do not only want to know how many substances are regulated, but we want to know their structure as well. Structural information is very rarely given in inventories. That's something that we get from somewhere else. What is given in inventories is information like a chemical name, sometimes a formula, CAS registry number, abbreviations, etc. But we need to be able to take this information and then look up a structure somewhere. In this case, we use a bunch of freely available tools like CAS Common Chemistry and PubChem to essentially translate chemical names or CAS registry numbers into chemical structures. When it comes to the chemical structures, we were, for the entire project, not only the chemical structures, we were very, very focused on providing really something that adheres to the FAIR principles like findable, applicable, interoperable, and reproducible. And so for our purposes here, we defined we used chemical structures in terms of the InChI string as a ground truth. We use that over, for example, smiles or other representations here. There are pros and cons to every chemical structure representation, but here we are just sticking to the InChI string. And so with this in mind, we set out to create both a fair, but also very clean global chemical inventory. The clean part is referring to this very tedious approach that we took in cleaning up the individual inventory information here. To come from the information that we have in these inventories, like a name and a CAS number, to the final chemical structure for us, we developed something we've called the cleanventory approach. On the left-hand side here, you see a schematic of this approach. I should also say it's a simplified schematic of this approach. And for the next few minutes, I'd like to walk you a little bit through it to give you an idea of the complexity of the task. Now, we start from the bottom and we work our way to the top here. First, we start with the input information. This is what I've been talking about. For example, we have a CAS registry number, a chemical name, sometimes other identifiers like an EC number, abbreviations, etc. When you look on the left-hand side to the bottom, you see two boxes there that are connected. Let's just assume that's a CAS registry number and a chemical name. Now, again, in an ideal world, the information of the CAS registry number and the chemical name would always match structurally like one-to-one. That's sadly not always the case. So we use API services to take that information on the registry numbers and the chemical names and look up potential structures associated with this information. Here we have used PubChem, we've used ComTalks, CAS Common Chemistry, and Cactus because they are all freely available for everyone, so it adheres with the FAIR principles that I've mentioned previously. If you've ever used, for example, PubChem or CAS Common Chemistry, you know that when you search for a chemical name, for example, you might get multiple results back. And that is because the lookup services, for example, of PubChem, take your request, look at it, and then provide you with the most likely results. The good thing is that all of these API services and databases are actually quite smart and intelligent, and they give you a ranked almost result list back, which means that the first result that you get when you search for something was determined to be the most likely result for your request. The second one was the second most likely, etc. And when you look at the left-hand side now, you can already see how this complexity builds up when we have two sources of information, a name and a CAS registry number. Then we have 5 different APIs, lookup services, and they all provide partially different chemical structure results. So we are working with multiple ranks that are interlinked. We've then developed a algorithm to figure out the most likely chemical structure here based on a consensus ranking approach. So what we are trying to do here, we are trying to map a single inventory entry with a CAS number and a chemical name to one most likely structure, even though there could be several candidate structures here. We are then taking it over to other chemoinformatic tools like OpenBabel to split, for example, multi-component structures. Think of simple things like sodium, salts, etc., into their individual components. So we have a database of single component structures, but of course we retain all the information for the multi-component structures. And in case I haven't mentioned it, we also retain all the candidate structures in the third step as well. And with this, we have built the 0PM database, and I'd just like to give you a few numbers here. Right now, we have included 25 different inventories, and the number 25 is not really like such a large number, but just wait for the next few numbers. Because in these 25 inventories, we have over 500,000 of unique individual entries in there. And when we then break these entries down into what type of information is given there, abbreviations, chemical names, CAS numbers, etc., we look at over 1.5 million unique search terms here. That also highlights the need for doing everything that I've presented so far programmatically, because there is no way you can do that manually. These over 1.5 million search terms return then over 400,000 potential candidate structures, but they, of course, are narrowed down to the most likely structures, and these would be the 140,000 0PM substances here. So you see, we are going from quite big numbers to a little bit smaller, more manageable numbers. And a few words on these 140,000 0PM substances, just on what type of information we have related to them. Of course, we have the inventory information. In which inventory has this structure been found? Where in the world was that inventory, the different countries, the different regions, but sometimes also like when was this first put into an inventory, when we have the information available. We, of course, have all the identifiers and all of the structures. We have all of the identifiers from the original inventories, like the CAS numbers, the chemical names, etc. We do have the consensus structure that we used on this rank-based approach, but we also have all the candidate structures available. And finally, that's what we are currently working on. I should rather say my colleague Sivani is working on this, and she'll present in a few moments. We will also include assessments on the persistence and the mobility of these 140,000 0PM substances. Now, the database is currently available on 2 places. The first one is simply the website for the database, database.0pm.eu. The database has been up and running now for, I think, a few months, 3-4 months now, and so far we've gotten a good feedback on it, but of course we are constantly trying to improve the database. There There are some back-end issues sometimes, so if you encounter any bugs, just please let us know. I said previously that everything here was done in a coding approach, and you can find all the code, and if you so wish, you can also create your own clean inventory or a global chemical inventory from the code that we have provided on GitHub. And you can now also find the entire collection of the 0PM substances on GitHub. And sort of confidential and hot off the press, today I received information from an insider at PubChem that soon, within a couple of days, also the 0PM substances will be part of the classification browser there, which I think is very cool, and I'm sure a lot of people will find that very useful. And with this, I'd like to once again thank all the partners within 0PM and especially within Work Package 5 on substance grouping. And now I will stop sharing the screen, and I think we can open for questions.
Yes, thank you, Raoul. We can open it for questions on the first part of our webinar. There's been one question that's left open currently in the chat. It's from Bjorn Hitting, and he says, I don't know the database in detail, so please excuse if my question is not relevant. I wonder if you have also applied additional scaling, example by adding overall production volumes or comparable metrics so you could further prioritize. So this goes into prioritization. But you can mention what's on the database and maybe a few things about what we discussed in prioritization.
Yeah, so I think that's an excellent question because it goes into a lot of the things that we are currently working on. Aside from these P&M assessment, we are looking at production volumes. We are also looking at other grouping strategies. So their work is definitely ongoing. Like this is by no means at the moment finished product. Like this is under constant development here. It's a very good point. Yeah, no, and I can also just add on to that. Like this is part of the workflow also that we're doing with this is to first start with the identity of the chemicals that are regulated, and then the next part obviously would be from Sivani on which ones are persistent mobility, and then amongst those we are looking at other metrics to prioritize. So we actually look at things like volume as a final step, but you know, this is just a starting block to building this. No, so thanks very much. Bjorn Hitting says thanks for the answer. And I'll just say to everyone, if you have any questions on Raoul's presentation, please put them in the Q&A, and we have time for this at the end of the webinar. But just to make sure that Sivani has time to present her presentation, we'll now transition over to Sivani Baskaran to present hers. And during this time, we will welcome questions on Raoul's presentation and Sivani's presentation and return to those in the end. Okay, Sivani, I see your slides are up, so please take it away.
Great. Sorry, my mute button moved on me. But hello, everyone. Thank you all for coming and joining in live or watching this afterwards to hear about our approach on the global perspective on persistent immobility of regulated chemicals. So as Raoul hinted at, I'm focusing largely on the persistent immobility assessment of these chemicals. So just for background, these new hazard classes were introduced in 2023 to identify persistent mobile and toxic chemicals or very persistent, very mobile chemicals. So for mobility, we use a partition ratio called the organic carbon-water partition ratio. It's a concentration ratio at equilibrium between these two phases. And this is used to describe mobility because it's supposed to be able to identify potential chemicals that can enter into groundwater and contaminate drinking water particularly. On the other hand, persistence is defined typically using half-lives in the regulatory context. So if it exceeds a specific degradation half-life within a particular environmental phase. It's considered persistent, or things can be considered not persistent if they pass a ready biodegradability test. So there's two types of data with persistency that we deal with. But there are a number of challenges when we're talking about assessing these chemicals on a global scale. For one, there are 380,000 substances on the global chemical inventory, way more than that now. Most of those chemicals do not have easily available data. They don't have enough measured data or metadata. And the reason metadata is so important are because mobility and persistence are the metrics used to define those classifications, KOC and half-life, are very environmentally dependent variables. So these can change with pH, with temperature, even the soil type, the amount of organic matter, the type of organic matter, the structure and composition can affect it. Sometimes even the concentration of the chemical, the amount of enzymatic activity, or even the presence and absence of other chemicals and reactants can affect these rates. And so it's important that we keep that in mind when we try to move forward with kind of consolidating and doing this full-on consensus-based assessment approach. So I've mentioned that these are very environmentally dependent variables, and we actually see that in the environmental data as well. So for KOC data specifically, these are 4 different chemicals with reported data, and you can see that they span many orders of magnitude. And in particular, you can see that we also have sensor data. So data that is shown in the red or the blue, and they have a line associated with these points. And these are data that are just indicated to be less than a specific value, between 2 values, or more than a single value. So it gives you kind of a sense of where the KOC from that measurement or estimation is going to be, but it doesn't give you an exact point. And it's very difficult to take an average when you have all of this different types of data. So we have to take a more kind of nuanced and more structured approach when we handle all of this. And this is where I'll talk a little bit more about my Bayesian approach to handling all of this data. Another important factor is tautomers. So in the case of the global chemical inventory, all of the chemical identifiers are reported in their final state as an InChI. And InChIs are great because they give you a lot of structural information. But for QSARs and running predictive models, we actually need the SMILES. And when you convert from InChI to SMILES, there's no guarantee that you're actually going to get the most likely or most relevant, environmentally relevant structure. So in this example, atrazine's InChI can resolve to this structure in the SMILES format, but it can also result in one of these SMILES as well. And while the structure on the left is most common and the one that's most environmentally relevant, we do kind of need to account for this because we're working with so many chemicals and so many different structures and types of chemicals that it's very difficult for us to go through and identify what tautomer is, what SMILES and what tautomer is the most environmentally relevant. So this is why we also take into account tautomization in my workflow. So what is this workflow? What substances am I actually working with? So in the Global Chemical Inventory, or GCI, we had about 383 substances when I started this project. It's since grown, but from there, I've separated and identified unique substructures. So this is removing salts and removing any duplicated identifiers that when I just pull the InChI, it's marked as such. I also remove any chemicals that are considered inorganic or I have isotopic information. For example, a deuterated chemical is just dropped or converted to the non-deuterated form. I also remove organic metallics, and so this leaves me now with about 233,000 structures, substances to be analyzing. But as I mentioned, it's really important that we're doing some tautomization as we move from InChIs to SMILES. So if I tautomize, I'll basically calculate tautomers for all of these different substances. I end up with 36 million different SMILES, and that's quite a bit. And so a large part of this is due to the size of chemicals. So if we remove any chemicals that are larger than 1,000 grams per mole, we actually account for 98% of the tautomers, and this is all just because there's more opportunities for tautomerization to occur. We further decided, because 440,000 chemicals or SMILES is still a lot to be working with, we brought it down again by limiting our analysis to 500 grams per mole or less. And then for the sake of statistical analysis, we also just did a selection of 5 tautomers per chemical at the most. So at most now we have 5 different SMILES accounting for a single chemical, or we have 1 SMILE accounting for a chemical. So each substance is represented by either 1 to 5 SMILES. And then because about 300,000 SMILES is still quite a bit, we further decided we're just going to limit our analysis in this instance to 120,000 SMILES that represent about 93,000 0 PM chemicals. So this is a simplified example of the analysis that we do for one prediction technique in the mobility assessment. So we now have 120,000 SMILES. We run all of these SMILES through Opera, and for each of these SMILES that we get 1 KOC prediction, along with some errors, standard deviations, applicability domain information, etc. Then we combine the SMILES, or the KOC values that we get for each of these SMILES, into a distribution for each substance. And this gives us a distribution for each substance for 93,000 substances. And we do the same thing again for a number of different models, and each model has its own unique features, their own pros and their own cons. There are different applicability domains, different considerations, and functionalities that allow us to predict a different number of KOC per SMILES. So each prediction is going to be unique, and so we can combine this all for each substance still in the end, so that we end up with 93,000 distributions for each of these models. Now we have all of this estimated data. We actually want to combine it with the experimental data that we collected. So I went through some of the larger literature data sets on KOC data to collect as much as I could, but I also went through regulatory data sets, particularly using eChem portal, QSAR toolbox, etc., to pull all the available reported KOC data. Based on this, and by combining with our estimated KOC values, I can do a probability distribution per chemical now on the KOC. And because we're working with probability distributions, we can actually do a lot of fun analysis in this instance. So for example, if I only consider the minimum of the distribution, this is what the KOC values sort of look like for all the substances we analyzed. And we see that most of these chemicals have a log KOC less than 2, would be considered very mobile, if only we use the minimum of the distributions. If we use the mean of the distributions, we see a very different picture. And this is sort of what you would expect when you're thinking about a distribution. And now we see that most of the chemicals have a KOC that is going to be greater than 3, and so are considered not mobile. If you consider the maximum, this changes again, but again, now we see even more of the chemicals have a log KOC greater than 3 and are considered not mobile. And what's useful also about this, but you don't see in this diagram here, is that we have some confidence, and we can assign some confidence to these assessments of whether a chemical should be considered mobile or not mobile, or very mobile. And that could be used to help prioritize whether this chemical needs to go for further testing, does it need more accurate experimental data, and so on. So as you can see, the endpoint of our selected assessment does really make a difference. And so here's another example of another way of visualizing this. The distribution in the background there that you see following this black line here is just an example. And you can see if we use only the minimum value, the percentage of substances considered not mobile, or sorry, very mobile in red, or is very high. But as soon as you use the maximum value, it's very low, and the percentage of chemicals considered not mobile increases substantially. So ideally, we will probably use a mean or a median, a central tendency to indicate whether a chemical should be considered mobile, not mobile, or very mobile. What I haven't mentioned yet, or I've sort of hinted at earlier, is the applicability domain of the models. So in this example, in this plot here, I'm showing all of the available predicted values are added to the analysis and used just without any kind of consideration on whether the model considers that value to be reliable or not. This is not if we change what input parameters we put in, so this is just shifting a little bit, the difference is not huge, but you see that there is more chemicals that are considered now a bit more mobile. If we only use data from chemicals that have or chemicals within the applicability domains of the models. This, of course, does not account for the fact that many of the chemicals probably don't work on many models, so there's a loss of information, and that might also artificially inflate the number of chemicals that are considered mobile or not, or very mobile. But it's a point that we are processing or will be considering in our analysis as well. And this is just an overview of the models and their applicability domains on the chemicals that we analyzed. So as you can see, EpiSuite fails really for many chemicals, and that is also true for the Franco and Trapp equations. And these applicability domains are more limited compared to the other models, which is why this occurs. On the other hand, Q-Surins performs really, really well compared to, or most chemicals appear within the applicability domain of Q-Surins. For ACD labs, on the other hand, it's important to note that there is very little information about applicability domain information, and so we just consider all the chemicals that produce a prediction from ACD labs to be part of the applicability domain of the model, which is why there is no difference in those two parts. And now I will quickly move on to persistence. So persistence data, as I mentioned before, includes binary ready biodegradability results that indicate if a substance is not P. And as a result, you usually have something 1 or 0, ready biodegradable or not ready biodegradable. And what that really tells us if a substance is not P, particularly in the context of our analysis right now. Getting a 0 result just indicates that it's potentially persistent, which is basically not enough information to make an assessment for the use of our models. So from there, we also have half-life data that is specific to different phases or a different system. And then we can use those half-lives to compare to the regulatory thresholds to identify chemicals as not P, P, or VP. And here we use a very similar process. We take 120,000 smiles, we run it through a model. We get a result, so in this case, a ready biodegradability result from OPERA for each of these smiles. And we can calculate a distribution. But this time our distribution is a probability of whether a chemical is going to be considered P or not P. And we ultimately do this for all of our substances to get a probability, ideally for 93,000 substances. And this approach is then again used for EpiSuite. OPERA has 2 models as well, so it has a half-life model that we use as well for each smiles. We can combine all of this information together to use with the regulatory and experimental data. So that's the next stage where we take the experimental data, the regulatory data together, combine it with the estimated values, and then are able to predict whether chemicals fall into one of these 3 categories. So this is an example of one of the probability distributions that resulted in our testing. So in this case, this chemical is considered not persistent. It has a higher than 80% probability of not being persistent. Whereas in this case, this chemical is considered to be likely to be persistent or very persistent, and as a result, probably requires a bit more testing because it's sitting around the 50% mark. Here is another example of kind of a subset of the data that we've been working with to test our methodologies, where we see the probability of the substances that are P or not P. What's also interesting is because the lack of available data, a lot of our results indicate 50%. So probability or around 50% probability of persistence. which is not useful, but it's not useful immediately, perhaps, but it is very useful in prioritizing chemicals, what needs to be tested further, what needs further analysis, maybe a closer look at the experimental data as well. And this is another way of looking at the data, same subset of data, and this is now looking at the probability of chemicals not being P, and you see the distribution changes quite a bit. So with that, I'm happy to take questions. Also want to acknowledge all of the people within 0PM, particularly Work Package 5, that help with this project, and my colleagues at InChI, as well as to Nizam at InChI, who helps a lot with the Bayesian analysis approaches and the computational resources that are available to us. So thank you.
Okay, great. Thanks, Sivani. So now we are opening the Q&A section of this webinar. So there's not that many questions in the Q&A, so I encourage anybody that has any questions, big or small, hard or difficult, to put them in. We'll see if we can answer it. There's one question in there now for you, Sivani, and that is, it's by an anonymous attendee. Could you please define how half-life affected by the concentration? So I guess this is about the persistency assessments and the data you chose. I think for a first order reaction, the half-life is independent of the concentration.
Yes, so this is not something that I will say that I'm a full expert on, but based on the literature I've read, you can actually get very different. Sorry, not for half-life, but for KOC specifically, or I'm talking about where concentration is dependent. So, for example, there's a model that shows that collected data from of samples in peat, and they use low and high concentrations of the same chemical, and they calculated or measured different KOC values, and were able to actually develop two separate models depending on concentration. So this is not relevant to persistence, but it's relevant for mobility. And so that summary was really to acknowledge both parameters are a little bit nuanced when you think about it environmentally.
Yeah. Yeah, no, and I'd add that onto it also by persistence. I was just seeing there's a work from in Stockholm University by a PhD student called Run Tian, who looked at the effect of spiking levels in OECD 309 tests, which is used to assess persistency in water. And there you see, like, once you spike to a certain extent, you can get actually more rapid degradation rates, because that becomes, it goes from being a minor food for the bacteria to a major food source, and then they will evolve quickly to degrade it. So there is an interesting spiking level question. So I mean, they recommend, and I mean, this is an open discussion in the persistence mobility community, if we should use like low concentration data, because low concentration data for persistence will give you this, say, conservative, longer degradation life, half-life. And similar with mobility, when you get to low concentrations, they refer to that sometimes as infinite dilution. You're in the linear absorption range, like with the example of peat that Sivani mentioned, and that is maybe better data to use in an assessment context. But this is, of course, a discussion that's going on now about assessing. So there's a nice, it's an interesting discussion that we're having on these topics right now. So, all right, new question. So again, from an anonymous attendee, can you give any insight on setting up any critical limit for KOC for a large number of persistent chemicals, or is it depending on nature, structure, fate, and the environment?
So maybe I can say that we haven't gotten to that stage yet, but once we have the full analysis with the persistence and the mobility done, I do want to do like a cross-sectional probability approach to see chemicals that are probably mobile or very mobile, are they also probably persistent based on our analysis? But it's also important to keep in mind the number of chemicals that we can assess with persistence is not as high as the number of chemicals we can do an analysis for with mobility. So there's also a discrepancy in the availability and applicability of data because of the model capabilities that we have right now and the lack of like kind of really good quality data sets on persistence. But if anyone has any that they would recommend, I'm open to adding more information to my analysis, particularly for persistence. Mobility is in the process of being wrapped up now, but definitely for persistence, if you have more data that can help us with this analysis, that would be great. I will maybe address the other question that was asked earlier as well.
Yeah, I'll just read it for you, just if you don't mind. This is from Johannes. How did you treat possible conflicting data between ready biodegradability and half-life data, for example? And I mean, maybe you can share some of your anecdotes about weird experimental persistency data we saw reported. Yeah.
Yeah. So it's actually quite tricky, but it's also why the Bayesian approach works pretty well. So for persistency data, for example, the first step that I do is actually just categorize half-life data is it greater or less than a threshold? And so is it considered persistent or not persistent? So I start with that, and then it's easier to combine the data with ready biodegradability because it's somewhat similar in its form. It's just saying, is it not persistent or persistent? And if you think of it this way, then you can also do some kind of Bernoulli analysis. So it's basically getting a probability of between 0 and 1, where 1 is it P. And I provide details regards to counts. So ready biodegradability indicates that it's not P, so it shifts it lower to 0, whereas maybe a half-life greater than 40, for example, 40 days indicates that it is P. So it combines all the available information into getting this kind of a range between 0 and 1 on the probability of P. So I do this approach for P, and then I do this approach for P versus VP, depending, again, very much dependent on the availability of information. So the VP data can only be assessed based on half-life. I can't use ready biodegradability for any of that.
Okay. No, and I think it's also very innovative in this approach that we are expressing probabilities of persistence and mobility, because then it's maybe different. The other discussion is like, where do you want to be confident in your own assessment of the chemical? Maybe some people want to put a prioritization at the 80% or 70% for their prioritization work, but this is something that we're having internally, but also something that we'd be interested in discussing with the wider community later. Now we get some questions. So this one is from Jamie De Shepherd. When you discussed using the models for KOC predictions, you mentioned that you considered the applicability domain of the models. Was this also the case for the half-life predictions?
Yes. So I didn't mention this, but it's because of the nature of the KOC value, it's way easier to kind of add errors to KOC values. It's kind of impossible to add an error to ready biodegradability. But that being said, for the persistence data, where the way that I'm handling the analysis with regards to applicability domain is also adding or removing data and seeing how that changes the results. Because there's no way for me to kind of look at a ready biodegradability result that is outside the applicability domain and add an error. And then with regards to half-life predictions, because of the type of methodology that I'm using, just kind of categorizing the data, it's not always so easy to include the standard deviation of the half-life when you categorize something as persistent or not persistent. So I'm more so using, is it within the model's local applicability or global applicability domain, and using it as a threshold of during the analysis and doing more of a comparative result rather than a numerical one in this instance.
Great, thanks. The next question from an anonymous attendee. How do you weigh the QSAR P and M results against published PBT VPVM results or PMT VPVM results provided by worldwide regulatory information or in experimental scientific articles? Example, if your QSAR results don't flag it, but ECHA does, would you include this?
So I am not using any categorical information in that sense from regulatory data sets. I'm using quote unquote raw data because the raw data is also quite messy. So when I pull the data from eChem portal, it pulls the data from the dossiers themselves. And this dossier result can include calculated values. It can include measured values, but they're not always reported, or it's not that they're not reported correctly. It's that the way that the data extraction occurs, and because there's such a large data set and dossiers are complicated, when I extract the data, it's not always clear whether it's actually an experimental result, even though it's reported within the Excel file as such. But if I go in and look in the dossier, I've found data that was, for example, I had found experimentally reported value of -20 KOC value, log KOC. And so I know this is impossible to measure. So when I go and look at the data, I see that it's like calculated based on this extrapolation methodology, and it's within the dossier, it indicates that it's not reliable. But just the methodologies for extracting the data that are used, it just doesn't work always in the best way. So I do weight the regulatory data that I've extracted a little bit lower, and I add a bunch of errors. So for experimental data too, I don't have any reported errors. So I add, for KOC specifically, I'm adding error, an assumed error for that. I'm adding an assumed error for the regulatory data. And then I'm ranking a little bit on the QSARs as well, based on my own reliability. For example, for EpiSuite, I will add a bunch of error because I know that it's not as reliable as some of the other methodologies. And I don't want it to outweigh the results because the EpiSuite result indicates one or matches particularly well with another value, or is consistent for like all 5 smiles that are run on a single chemical. So I do my best. It's not no approach is perfect, but I try to approach these as well as I can. But to answer, going back to your question, I don't compare the PM guidelines strictly, at least not yet.
Great. Okay, the time is still open for more questions. I'll just also say where you can learn more about this from 0PM is that we do also have some materials posted on our YouTube channel and website where you can learn about the work of Raoul and Sivani and others in 0PM. But for this work specifically that we're doing, in addition to consulting the 0PM database, we are working on manuscripts that we hope to finish within the next month or 2 or 3 about all this work that'll be presented today. So that will be out there. And then ultimately, the probabilities that Sivani was presenting for persistence and mobility will be available on the global chemical database. So that will be available for consultation from users around the world for their work with persistent mobile toxic substance assessments. And as I see no further questions, I can also maybe give a sneak preview of our next webinar, which will be a science and policy webinar, likely on January the 22nd, correct, Sarah? January 22nd is a tentative date. It'll be around the same time, and it will be with Magnus Lofstedt from the European Environmental Agency, about the work of the European Environmental Agency related to PFAS in Europe and how they're addressing PFAS issues, including the broad PFAS restrictions. So note that down before we send out the invitation. So that's on your calendar. And I don't see any more questions, so we've resolved them all. But if there's any questions to Sivani or Raoul, just send an email and we'll be sure to give it our attention. And I think with that, I will conclude this webinar. So I thank you for your attendance today. I thank you for the great presentations and work from Raoul Wolf and Sivani Baskaran presented today, and my co-host, Sarah Hale. Thank you, and also our technical guy, Johannes Aumann in the background. And thank you for watching, and thank you for this 0PM webinar.
Thanks all, bye-bye.
0PM. Zero pollution of persistent and mobile substances.
This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under grant agreement number 101036756.